Okay, to this example, we will compute the forward-backward difference approximation of OH and OS square. Okay, so then we will use high accuracy also. And central difference approximation of OS square and OS power 4. That is the more accuracy also. Okay, for first derivative, just only first derivative. For this case, that's only first derivative. And we estimate the true percent error. True percent error is mean the error comparison with the exact solution. Okay, true percent error is mean that we know the exact solution, right? So for this case, we have to determine the exact solution first. Okay, so for the case of C, log x, okay, y equal to log x. So what is the exact formula for y equal to log x? The first derivative dy by dx is equal to what? Who know, please? What is the exact solution? What is the exact formula? What is that? Who know? What is that? Please. I will wait. We will solve for this problem, that is y equal to log x. Y equal to log x when x equal to 25, right? Okay, when x equal to 25. And we will apply for the problem that we would like to apply high accuracy also. For high accuracy, we have to determine xi plus 1, xi plus 2, xi minus 1, and xi minus 2 also, right? Okay, so it should be, I may create a table like this, and it should be xi. Xi is maybe over here, right? Okay, it's xi minus 1. It is xi minus 2, right? And this is xi plus 1. And it should be xi plus 2. Okay, xi is become 25. Okay, xi plus 1 become what? Okay, I just would like to change. H is become 2, right? Okay, so then xi plus 1 is equal to what? It's equal to this plus h, right? And it should be this plus 2h. You're right. Okay, it should be the same. X minus h, and it should be x minus 2h. You're right. Okay. After that, the exact value is what? It is the exact value, right? We use this formula that is equal to what? 1 over x. Okay. 1 over x should be multiplied with log 10, right? Log 10. You're right. It should be over here. Okay. And okay, actually it is equivalent with 1 over x, or another formula 1 over x times log, okay, log 10, right? Be the same, okay, because this is the inverse function of that value. Okay, so we already have the exact solution, right? This is the exact solution in this case. Okay, and then the approximate one, okay, we will determine the first derivative of y equal to log x. Sorry. Okay. This is for function, right? Okay. Function is equal to log x, log 10, right? Let's be 10. You're right. We have this value. You're right. Okay. So then we will use the forward difference first. Okay. For forward of OH. Forward of OH, dy by dx. Approximation is what? This formula, right? This is for forward difference. We use the forward value. Okay. That is equal to what? It's equal to fx. Okay. Fx plus 1 minus fx. Okay. Divided by h. Right? Okay. So we count like this. Okay. And what is the percent error? Percent true error, we compare with the exact solution, right? About 3.79%. Okay. This for forward difference. And if we determine for backward, or forward, maybe like the pink one, right? Okay, for backward. Backwards of OH is what? For backward, formula is what? It's over here. It's backward, right? Backward is become what? Is fxi minus fxi minus 1, right? fxi minus fxi minus 1. Okay. And divided by h. Okay. It's become like this. And okay, 4% error is equal to what? Okay, it's about 3% or 4%. Okay, for this case, I use the blue one. Okay, and for central of s squared. Okay. Become what? For central difference. Formula is maybe like this. Okay. For central difference, we have to use both fxi plus 1 and fxi minus 1, right? Xi plus 1. Okay. And fxi minus 1. Okay. Divided by 2h. Then we have this value. Okay. And percent error is okay. It's about 0.1%. Okay. I represent this like the yellow one. Okay. You all right? This is just for the general case. Okay. We move to high accuracy. Okay. For high accuracy, it should be like this. This high accuracy is about OH2 rate. Okay. We do the same thing, but with another formula that is maybe just like this. We use this formula instead. Okay. So what is that? The first forward difference is become what? It's become minus fxi plus 2, right? Okay, plus 4 times fxi plus 1 minus 3 times fxi. Okay, and then divided by 2h. Okay, it's become like this. So should be this value, right? Minus this one. Okay, divided by this one. Okay. Sorry. The error is reduced to 0.3599%. Okay. So then we will use backward. For backward, which OH2 that we apply for high accuracy. Okay, this become what? This become 3 times fx, okay, minus 4 times fxi minus 1, right? Okay, plus fxi minus 2, okay, divided by UH. Okay, percent error is become all right. Okay, the percent error is reduced from 4 to be 0.5. Okay, and then you do next for central difference. Central difference, it should be over here. Okay. Central difference, the formula is what? Okay, now central difference is OH powerful, right? And the formula is become, okay, minus fxi plus 2, okay, plus a times fxi plus 1, okay, minus a times fxi minus 1, okay, plus fxi minus 2, okay, and divided by 12h. Okay, right here. And what is the approximation of this? Is equal to okay, it becomes 0.003%. Okay, are you all right for the first example? Are you okay for that? The first example. Are you okay? It should be all right. Okay, then I think for another function, you may do it by yourself, right? Okay, it just should be the same thing. Should be the same. But if we approximate, if we use this sheet, actually it's maybe easy to between. I think it's maybe all right. Okay, so if we copy this, okay, this for the case of C, right? And if we do the same, no 1A, it may be easy to begin, right? No 1A, no 1A is what? Do the same. 101A is y equal to sine x. Okay. Y equal to sine x, exact solution is what? Easy, right? Y equal to sine x. So the exact solution is become what? Exact solution. What's that? And x is become pi over 4, right? Okay, and h is become pi over 12. Okay, that's all. All right. Okay. So what is the exact solution, please?
พอร์ต x ว่าครับ
Cosine x, right? Okay, so we already done, right? Okay, that's all. Easy, right? That is for the case of function is equal to y equal to sine x. Okay, we can approximate the function, the first derivative of this function like this. Okay, you're right. Okay, so we have just 1 minute. Okay, we can do for last one. Do the same thing, right? But we change the function to be what? To be cosine, right? So the exact solution is what for this case? This is the negative, right? Negative sine x. Okay, and x is same, right? Pi over 4, right? And s is become pi over 12. It should be the same. And now just change. Okay. So okay, this should be all right. That's done for this case, for just the first problem. Okay, for the first problem, that it should be all right. Okay, so then before we move next, okay, you may do it by yourself first. For the second one it just should be the same, but you use the key number for this case also for a, for the value of constant a. That's just maybe next time we will moving to this example. Okay, in order to review what we understand for that. Okay, but for this case we will use just only central difference, because we know that it is the best one for this case. Okay, the central difference is the best. So we will use the central difference to approximate the first and second derivative. For this case, we use first and second derivative. Okay. You may do it by yourself. Just use just only the central difference. And now, before we finish, I just ask you a little bit for the case of this case. We don't have the function anymore. Okay, we have the tabulate. we have the tabulate data like this. Okay, we have the time and distance of a car, that is maybe tabulate like this. Okay, that is for the key number is depend on your number, right? Okay, so if we would like to approximate the velocity and acceleration at each time of this car, how can we do? Okay, just answer me just only the idea, right? That is what, how can we do for this case? What do you think? We have the tabulate data like this. We have time as 0, 2, 4, 6, 8, and 10. What do you think? How can we do this? We would like to find the velocity and acceleration. Velocity is what? Velocity is what? Y over t, yata is just is maybe is for that case it's just constant for the constant. Okay, first derivative of this 10, that's all right. That's all right. Kin, this is very good. The first derivative of this 10, this is all right. Okay, we have to determine the first derivative of this 10. So that we have to find y prime, right? Y prime. So how can we determine y prime? That is the first derivative for that case. And for the acceleration is what? For the acceleration, velocity is the first derivative of y. You take Tanacho, you take the first derivative to v again. That is mean that it is the second derivative of y, right? Okay, it is the second derivative of y. So that's why for this case we would like to find v is equal to y prime. Okay, and a is become y, second derivative of y. Okay, so but we have the data like this. So what do you think? You will use forward, backward, or central difference? What do you think? Forward, backward, or central? If we just mention for the case that the error is maybe just for the first case, that is maybe not necessary to use high accuracy for the case, for the general case. So how can we do? How can we approximate the first derivative of this data? What type of formula we will choose? Forward, backward, or central? We may starting with this data first. If we consider the data of this value at 2 seconds, 4 seconds, 6 seconds, and 8 seconds, which formula will you choose? Forward, backward, or central? If you choose forward, stamp on the red box. If you choose central, stamp on the green box. Sorry. Should be here. Okay. If you choose backward, stamp on the blue one. For this data first, or just only 2 seconds, 4 seconds, 6 seconds, and 8 seconds. Which formula will you choose? Forward, backward, or central? Why no answer right now? You choose central, right? You use central. For 2 seconds, 4 seconds, 6 seconds, and 8 seconds, you choose central difference. Okay, why you choose central difference? Kin, why you use central difference? Why you choose like that? Why you choose central difference? No answer. Easier to calculate. Central difference, easier to calculate. Actually, both of all is just easier. It's easy, but actually for this case, that is you use central because of what? For 2, 4, 6, and 8. So then I will ask you again for if we mention to this point. For time equal to 0 second, can you use central difference?
No.
Can you use central? Cannot, right? We cannot because of what?
It has no data before 0.
Yes, it has no data before 0. So what formula that we have to use?
Forward.
Forward difference, right? Okay, so for the data f time equal to 0 second, we have to use forward difference. But the time equal to 2, 4, 6, 8, we use central difference, right? That is the error, the truncation error is around, is what? The error is for central difference. The error is OS square, right? So in order to keep the error in the same order, so for this data that we have to use the forward difference. We have to use high accuracy for this data. That is, should be used forward difference with OS square also. Are you alright? That we can, because we have enough data. That is, we have forward data. Okay, so what do you think for the case of the data of 10 seconds? If we would like to approximate the first and second derivative, which formula that we have to select? Which type? Backward, right? We have to use backward. We have to use backward with high accuracy also. Okay, with OS square. Okay, that is just the guideline for this problem. Okay, and for the fourth one, I will discuss. We will come back and discuss again on Friday. Okay, so that is all for today.